So, as she said, I will talk about foundation models in radiology. So I think it's the first talk about radiology here. So we're going to talk more about imaging and not so much about structured data or text here. So I will skip this as she introduced me. So I work at Radium. So Radium is a startup that was founded around 3 years ago, and we focus on radiology. And we are building a viewer for our radiologists. So it means like a tool where you can visualize your images, for example, scanners or MRIs. And we want to build a native AI viewer. So it means that it's integrated with the latest AI tools based on foundation models. We focused a lot on oncology for now, but we aim to work on also all the different areas of radiology. And here the goal of foundation models is that we want to have models that are universal, that are state of the art, and that also have the humans in the loop, which means that humans can interact with the models, can prompt them to do some tasks, and can also correct if the model's outputs are not correct, which was not really possible in the previous models, which are just input output, and you have to correct manually if there is an error. And so this represents the current approach in radiology. Basically, you have a lot of scattered tools because radiology is basically essential for clinical practice in medicine. You have like multiple modalities like CT, X-ray, MRI, scanner, ultrasound, etc. You have thousands of different pathologies that you can diagnose with radiology. And so you have to build one AI tool for every combination of modality and pathology and body part, which is not feasible in practice. And so this is where foundation models can be very helpful. They can be multitask, multi-organ, multimodal. So take as input, for example, CT, MRI, text report, indications, clinical history, and be flexible, as I said, take human as input and being able to fine-tune them for new cases, and also hopefully be used in agentic pipelines, so being used as tools called by a larger orchestrator. And so at Radium, we build foundation models for radiology. We focus on two areas. We have one which is frontier research models, which I will talk about more today. So we train foundation models and we release papers, and we release all our models as for open source. So you can actually use the models, try them on your own data, on your own pathologies, etc. And we also have application models which are directly put in the viewer for doctors, so detection, segmentation, longitudinal propagation, etc. And so, yeah, the promise of foundation models here for us, it's mainly those two: generalization. So they can learn a broad representation of the world. So the world here is the human body, and it will learn some emergent properties. So, for example, being able to generalize from one modality to another, being able to learn with very few additional examples for a new pathology. And also they can be multi-purpose, as I said, so being used for many pathologies, for many different tasks like classification, segmentation, survival prediction, etc. And so I'll talk now about one model family that we are building at Radium, which is called Curia. So Curia, the first one, it was the first foundation model trained on an extreme scale multimodal dataset of CT and MRI. And it outperforms previous models on a series of 19 different tasks. And the Curia 2, which is a follow-up work, where we improved the pre-training strategy, and it led to a new state-of-the-art. And so I'll detail now those two works. So it involves actually a lot of people, and as the previous speaker said, yeah, building foundation models is a very big like technical challenge. So a lot of engineers and a lot of doctors are involved in training this model. And first, to train the foundation model, the most important part is the data. And yeah, as Eduardo said, we need a lot of data. So we have a partnership with a private hospital from Saint-Denis in the Paris area, and we collected around 100 terabytes of data of CT and MRI images. So it represents around 200 million slices of images, and it's around 1 million volume. And so that's kind of similar to what the general image foundation models are trained on. I will explain it later, but we use DynoV2. It's a self-supervised training algorithm, and they have around the same amount of data for the natural image framework. So that's one of the biggest data that was used to train the foundation model in radiology. And so yeah, we use this dataset to train the model, and it's so yeah, previous foundation models like Biomeclip or Medimage Insight had much smaller datasets, and it covers the whole body, thorax, abdomen, head, and etc. So it's very diverse. And we use the architecture of this model is a vision transformer, so it's a very standard deep learning model. The image is divided into a set of patches here that are projected into a token space, and then a transformer processes them and returns new tokens that have to represent the semantic content of the image. And we train them using the DynoV2 algorithm. It consists of multiple different losses. The main idea of those losses, so I won't get into too much details, but it's to learn the internal structure of the image. And so there is a patch level loss, which is basically you hide some part of the image, like you blacken them out, and the model has to learn to repredict them in the output. There is an image level loss, which is contrastive, where you basically create two versions of your image with different transformations, like rotations, crops, etc. And the model has to learn to project them into the same features. So it learns the model to be agnostic to some kind of transformations. And then there are a lot of regularization loss to avoid the model to the collapse. And so, as I said, it forces to be that all the images, it forces the model to learn the structure of radiological images. And so, to evaluate the model, we introduce a benchmark which is called the CuriaBench, and it's a set of 19 downstream tasks. And so we aim to set a standard evaluation benchmark for future works on the foundation model for radiology. And it covers a lot of different medical areas like anatomy, oncology, musculoskeletal disease, emergency, neurodegenerative, and infectious disease. And so, yeah, you can see here some example, for example, CT organ recognition, stroke prediction, age estimation, hemorrhage, etc. So it's very diverse across the body and across the modalities. And so we evaluate our model and other foundation models on this benchmark. It has some classification, regression, survival prediction, and segmentation tasks. And also we evaluate few shot and cross-model settings. So I'll get it also in more details after. And so to evaluate the models, we use quite a simple setup because we want to evaluate the model's features. So we don't fine-tune the model, we just freeze the foundation model here and we extract the features. And we just train a linear classifier on a specific task, for example, stroke prediction here. So we have the labels for the downstream task, and it's like a few hundred images. And for some tasks, we actually have a mask here that describe the region that the model has to look at. So here we just feed the whole image to the model. It doesn't see the mask, but then we just take the features inside the mask, average them, and train a linear classifier on top. And it can be, for example, organ classification. Here we see the liver, so the model has to output this is the liver. And so as I said, we evaluate the model against previous foundation models, so Medimage Insight and Biomeclip from Microsoft. And those models are actually trained on a much more diverse set of modalities, not just radiology. They have also pathology, genetics, textbooks and stuff like this. So they are much more general, but and so they don't perform as well as Curia for radiology. You can see that Curia is much better for most of the tasks. And we also evaluate against radiologists. So we take a subset of every test set on the benchmark. We ask the radiologist to predict the correct label for all those images. And we can see that Curia is usually significantly better, or there is no significant difference between the radiologist and the model. So yeah, that's very promising for clinical applications of foundation models. And so, yeah, as I said, the models, foundation models are also usually known to be good at few-shot learning and generalize in cross-modal settings. So, yeah, this is the case here. We can see that we're using even only one example for each class. The model is already much higher, much better than other foundation models or that a model from scratch. And with like around 10 examples per class, it's reaching almost the peak performance here for organ classification. And also one very interesting observation that we didn't really expect when we first trained the model is that it actually has very similar representations for CT and MRI for the same organs and the same pathologies. And so if we adapt the model using linear probing for CT, so here again for organ recognition, and then we evaluate it on MRI images, we only lose 10 points. And the MRI task is actually a bit harder. The model, all models perform a bit lower, so that's expected. And this is much lower loss of performance compared to the other foundation models, and also a model trained only on CT images, which cannot complete the task at all. And yeah, we can see this quite well when you look at the feature representations. So here we just take the output features and we do a PCA on the features on 3 dimensions. And we can see that for CT and MRI, so the model has very similar representations. So here we can see, for example, the kidneys in purple, the bones in blue, and they are assigned similar colors, so similar features compared to other models, which the representations are not so much organ-based, and it's not very clear what they are learning. But yeah, they don't have so much similar features between the images. And so I'll do a quick follow-up on on Curia 2. So Curia 2 is actually a very similar work. It's the same pre-training method, so DynoV2, and it's the same data set, but it's mostly about methodological improvements to the pre-training. And because one particular aspect of medical images on CT and MRI is that they have a lot of dark regions around the image, which is not the case for natural images, for which DynoV2 was created. And so when we use the regular DynoV2 framework, it will create a lot of crops, which are zoomed portion of the image in dark regions like this. And this is not very good because then the model has to learn to predict some structure from just a dark patch, an empty patch, and it leads to a lot of model instability and collapse during the training. And so we introduce 2 improvements. The first one is the content-aware cropping, where we basically just take only crops inside the actual content of the image. And a second one is anatomically guided masking, and similar is for the similar reason, but this is for the loss that will mask some portion of the image, and the model has to repredict the masked region. And so we force the model to, like during the training, we force the masking to happen inside the body and not in the air. So the task is not trivial, and it's just predicting some dark pixel. And so yeah, it's beats Curia 1 on the public benchmark on CuriaBench that we released. And so yeah, what makes this model unique? So it's one of the largest real-world data that was used to train a radiology foundation model. It's a event transformer architecture. The pre-training is quite large scale. It's 5 days of training on 32 GPUs. So we use the public infrastructure, IDRIS and Euro HPC to train those models. So yeah, we thank them a lot for this. And we released the benchmark and the model open source, so they are accessible on Hugging Face, and you can see the demo on the website and a research paper. So yeah, this is it for Curia. Oops. And so then I will give you a bit of details about the current work that we are doing. So all the previous work on Curia, we used only the image. We never used any textual representations, any labels, but we actually have access to a very big source of labels, which are the radiology reports, because all studies that are done in radiology are associated with the report, which is quite long. It can be yeah, like 1 page of description of the image, organ by organ. So it's yeah, a huge source of information. And so the current work that we are trying to do is to leverage this textual information to improve the foundation model's representation. And one common thing that is done in radiology to train a foundation model is to use CLIP. So as you see on top of it, the global alignment. So you do some contrastive learning to align the features that come from the vision model to some features that come from a text model. And so you compare the two with for example, a cosine similarity or some loss to bring the two features closer together and to bring features from different unpaired pairs away from each other. But this loss was built for very short captions usually, because you have one vector to describe the whole image, one vector to describe the full text. But here we have 3D volumes, which are huge. We have a text report, which is like 1 page of very detailed caption. And so it doesn't work so well if you use CLIP, because then it has to fit a huge amount of information into a single vector. So it works for captioning, for medical, for natural images, but it doesn't work so well here. And so we introduced per concept alignment loss, where we just extract some region-based text from the report. For example, everything that describes the heart, everything that describes the trachea, the bones, etc. And then we learn some queries on the image side to extract the tokens that are, so the image regions that are interesting and that are related to this text section. And then we align each one of those sections separately, in addition to aligning the global representations. And so, yeah, this leads to a lot of improvements for the pre-training. And there is a preprint that will come soon with more details. And yeah, so very quick overview of the results. We evaluated on findings classification. So we have a list of like around 300 classes of abnormalities that can be seen in CT images. So here it's only CT. And we print we show here the AUC, the macro AUC, so the average on all the findings, and the model yeah, outperforms Pillar 0 and Merlin from Berkeley and Stanford, which are CLIP models, so trained with alignment of global representations, and also on report generation, so trying to predict the full report just from the image, and here as well the model performs much better. And so, yeah, this is more like the direction we are looking at Radium for AI in radiology. So all those models, they are really useful, but we think that they are they will be useful in the future as tools, actually, that can be used by radiologists, but also by an orchestrator and LLM pipeline. And yeah, that's the things that we are trying to build at Radium, and we are thinking a lot on how to evaluate and how to benchmark those agentic approaches. And so, yeah, this is our also future work on how to unify all those pipelines like detection, segmentation, findings generation, report generation, etc., and having a very integrated pipeline, and that the human can control very easily and correct and ask some questions, etc. So yeah, thank you.
Okay, so now we have some minutes for questions. Does anybody have any questions for Corentin?
Thank you for your talk. I have probably thousands of questions, so I will skip them. But one key point is your last model, where you want to have multimodal. It's multimodal approach, and I find very interesting. I understand that you put image and you have learnable queries. So I'm not sure where is the text there, but I assume one query is more for the heart,
Yes.
stomach, and so on. You want to learn some feature. And can you, I don't know if it's a place for that, but go into a little more detail. Thank you.
Yeah, sure. So actually, some previous works were tried things like this to align per concept, but they used segmentation masks. So they ran a segmentation model. One is called total segmentator, which is very common in radiology, which gives you a mask for each organ. And then you can maybe do some pooling of the features for this mask and align. But it's not very flexible because it's a fixed list of classes, and it's very long to like the model is very slow. So it's if you have millions of images, it's very annoying to run each time. And so here the queries are just some vectors that they are learned during the pre-training. So the only source of how will the model learn to align like heart with the query one is because there is this alignment matrix here, and so yeah, the model needs to predict what's in the heart based on the attention here coming from the visual features with this query. So naturally, it will learn to select the right tokens that belong to the heart. And I didn't show visualizations here, but because we are writing the paper now, but if you check the preprint, which should be out in a few days, you can see if you look at the cross attention map here, that actually it focuses very well on the correct region. If you look at the similarity between the query and the patch tokens, so each query will learn to look at a specific zone which is associated with the text region that it's trying to be aligned to.
So this left concept make me think of DTR.
Okay.
You know this model, DETR?
Ah, yes.
From
Yes.
Facebook a few years ago.
Yes.
So, but actually, as you say, you don't learn from, they have learned ground truth from segmentation.
Yes.
But you learn from perplexity loss with the text?
No, here it's not perplexity loss, it's contrastive loss. So it's the clip loss, basically.
Ah, yes.
So yeah, we just forward this and it gives us a single vector describing the text. And yeah, we're trying to align it with the pooling, like the pooled patch features. Yeah.
Yeah, so
But
you have different clips
yes.
for different organs.
Regions, yeah.
Thank you
But
so much.
it's quite similar to Deter actually, but it's like semi-supervised because we don't know which region we are trying to see. But yeah, it's pretty close to Deter in the spirit, yes.
Thank you for the talk. I have a question actually because Dino was originally designed for 2D images.
Yes.
So I wanted to know what were the adaptation needed for training it on volumetric data, especially in terms of memory, because like CT scans are really big in memory on the GPU.
Yes.
And also in line with it, are you doing some specific pre-processing steps? Because you have a lot of CT volumes, MRI volumes. So yeah, just wanting to know what are the the pre-processing steps as well?
Yeah, that's a good question. And actually, the model is trained in 2D, not in 3D. So it's a very similar setup to Dino V2. And if we have 3D tasks, we just concatenate the features. We forward each volume through the vision encoder, and then we concatenate the feature into a 3D feature map, and we do some classification task on this 3D map. And it works quite well in practice, and we actually built some 3D foundation models using this approach. So yeah, the 3D is not necessarily like it's not essential to be as part of the main model. But we actually tried the follow-up works on 3D. We focused more on masked autoencoder models for 3D because it's much easier to train in practice and it's more stable. So and it led to some interesting work, but not it didn't outperform. It was very close to this in 2D. And yeah, for the pre-processing, we do very simple just Z normalization on all images, and yeah, not much apart from this. Because we want to have a very similar CT and MRI pre-processing, so the model can take both as input and both be comparable. Yeah, some work try to do windowings, clipping extreme values and things like this. But yeah, we don't do this in practice. Yeah.
Sorry, I have two questions. First is, did you try this on different types of radiology modalities, or like different types of CT, for example, CCTA, like specialized types of images, or did you just try it on MRI and the normal CT? And the second question is, have you tried it on like imbalanced data sets? How effective it is?
So yeah, this model is trained on like regular CT, I would say, and MRI data. So like yeah, mostly chest, abdomen, and head CT, and no specific kind of CT like arthroscan or yeah. I don't hear which one you mentioned, but yeah, it's like general CT and general MRI. We don't do like breast scan, mammoscan, and things like this, because yeah, those modalities are a bit different in terms of structure, and so yeah, we didn't look so much into this. And what was your second question? Sorry. The imbalance, yes. Yeah, for the imbalance, so the pre-training data set is not very balanced. You can see that thorax is a lot of data, and the rest is much lower because the hospital is kind of specialized in thoracic medicine. But it doesn't really hurt the performances like here for yeah, like hemorrhage, stroke. Like the model still learns to perform all the tasks quite well. And then for the downstream tasks, we haven't studied specifically. If you have a small labeled data set, we haven't studied specifically the imbalance. So yeah, I'm not sure how it performs in this setup.
Any final questions?
Right. Thanks. Nice talk. Just curious, did your work lead to software in the hand of radiologists that are actually used in practice, and did that needed some authorization from EMA, FDA, things like that, or?
Yeah, it's a good question. So this model was integrated into the product that we are selling to radiologists, but it's a research only tool. It's not yet marked for the FDA, like by FDA or the European Union. Yeah, hopefully it will be done. We actually at Radium still have we are quite a young company, so we don't yet have a marked device. So we are only doing research on the tools. But yeah, we hopefully very soon we will have some marked device. But we are focusing for now on the more specific models, like for the oncology workflow, that do like segmentation, detection of lesions, and propagation of masks through time to compare the volumes of lesions. Not for now, not so much on the very general foundation models, because it's very hard to mark at the FDA. No one yet has marked a foundation model that can detect 200 pathologies and predict some report. This doesn't exist yet in the FDA tools. So yeah, so very hard to mark. And if you mark a device, it's much easier to compare yourself to something that exists already. So there is nothing to compare. So it will be very long and expensive procedure, but hopefully we might be the first to do it. Or yeah, if someone else do it first, then it will be easier.